Hi there. In the last video, we had a look at the basics of probability and what it means to come up with some probability calculations and so on. In this video, we're going to specifically look at weighted trees. And I know that we've done some in-class work on this, so I'm not going to belabor the point too much. We're going to get straight into an example. But I guess if I was trying to sort of say when would you use a weighted tree, as I've got here, it's good for a multi-stage event. So when you've got this happens and then this happens straight afterwards, then that's quite of a good time to use a tree. And weighted trees specifically are good for when you have multiple bits to your event that can sort of be collected together, like 3 red balls and 2 blue balls in a bag. Then you've got 3/5 of a chance of pulling out a blue ball and 2/5 of a chance of pulling out a red ball, that kind of thing. But I've got an example here we'll go through. And in this instance, we're sort of given the calculations already, so it's not too bad. So 2 games of hockey are played. The probability of a win is 0.6. What's the probability of at least one win? Okay, so I start by generating my tree, and I start with a little dot for a node, and then I put in 2 branches like so. Try and keep the branches fairly well spread out. And I'm going to call W for win and L for loss. And so this is an outcome. So the outcomes go at the end of the branches. And then on the branch, we put the probabilities. So the probability of a win is 0.6. Maybe you might need to pause the video, or maybe you can just do it pretty quickly. So therefore, the probability of a loss is 0.4. Winning and losing are complementary events, except I haven't really talked about draws, so we'll just forget about draws. It's either a win or a loss. So they're complementary events, and so if they haven't won, they've lost. If they haven't lost, they've won. So they're complementary, 0.6 and 0.4. That's the stage one, though. That's the first game. The second game would be another branch coming from here, and another branch coming from here, another branch coming from here, and another branch coming from here. And again, for the second game, it's either a win or a loss. So what this means is that they may win, and then in the second game, they could win or lose. Down this branch is they may lose, but then in the second game, they can win or lose again. So you do need both sets of branches like so. And I'll put the probabilities in like I did before. 0.6 for a win, 0.4 for a loss, 0.6 for a win, 0.4 for a loss. So you can see that on the branches, and there can be more than 2, but this is just based on the example I've got. But each set of branches coming from a node has to equal 1. That's 1 there, that's 1 there, that's 1 there, a node or an outcome. Okay, then we can actually write the outcomes. These are, to be more precise, these are the unique outcomes. So the unique outcome could be a win followed by a win. This is the unique outcome, win followed by a loss. This is the outcome, loss followed by a win. And this is the outcome, loss followed by a loss. And do note that a win followed by a loss is a different outcome to a loss followed by a win. Okay, in order to calculate the probabilities, we run across the branches and multiply as we go along. So 0.6 times 0.6 is 0.36. Then I've got 0.6 times 0.4, which is 0.24. 0.4 times 0.6 is also 0.24, and 0.4 times 0.4 is 0.16. And it should be no surprise to you that if you add up all those numbers, you'll get 1.00. In other words, all of these probabilities combined is basically every single outcome, and therefore the total of those outcomes is 100% or 1. Okay, in terms of answering the question, it says, what's the probability of at least one win? Okay, so it's the probability of at least one win, and that is equal to, well, if we have a look at our tree, we need to match up all those where there's a win. That's at least one win because it's 2. That's a win, that's a win, that's not. So we're going to have 0.36 plus 0.24 plus 0.24. In other words, for each of my matching success outcomes, i.e. it's at least one win, I'm going to add them up across the branches. So I am multiplying along and I'm adding across. Okay, so 0.36 plus 0.24 plus 0.24, and that's equal to 0.84. Done. But there is an alternative that we could have used instead, and is a little bit more quicker to do. So pause the video and think, what's the other way I could have solved this? I wonder if you came up with this. So I'm going to put an or there. Or the probability of at least one win. It's a bit wordy to put this, but I'm putting it just for the sake of the notes, is equal to 1 minus the probability of no wins. Now, I'm putting this down even though this is a very straightforward problem, because this is a critical, well, it's a really useful strategy to have in your kit of things to do, particularly when you see the words at least one, or at least two, something like that. Often, it's worth spending a moment to just go, is the complementary of at least easier to calculate and then subtract it from one? It quite often is. In this instance, it's a bit of a line ball decision. But as you can see here, in this instance, I know what no wins looks like. It's a loss and a loss, and that's 0.16. So that's 1 minus 0.16, and that gives me 0.84, just like the other one did, of course. So 1 minus the complementary is frequently a quicker way of calculating the result than trying to calculate all the multiple outcomes that might match. You just need to be aware of that and be sure to look out for it. Okay, if you have a look in your work schedule, you'll see some work that you can do on weighted trees. And once you've had a go at that, come back and watch the video on Venn diagrams.